Okay, we are given a rule for a linear transformation, and the rule simply says that this linear transformation acts on a vector, and the vector would be a vector with two components, a column vector in this case. And the rule says that if this vector is v1, v2, whatever v1 is and v2, it's going to map onto the vector which is equal to v1 minus 3 times v2, and whose first component is v1 minus 3v2, and whose second component is v2 minus 2v1. And I said that wrong. It's 2v1 plus 2v2, and v2 minus 2v1. Okay, that's the rule stated in the document. So we translate that, and using that rule, it's very straightforward to calculate this, and we find that 2, 3 by the rule that's given maps onto the point -4, -7. Now, if you want to see the rule written out in vector form, the vector v1, v2 maps onto a vector with first coordinate v1 plus 2v2, second coordinate v2 minus 2v1. That's the rule. Okay, so applying that rule to the vector 2, 3, we just plug in 2 and 3 and we get this result, which means that we can take the vector 2, -3 here, okay, and it maps onto the vector -4, -7. Now what happens in that mapping? It looks like this vector gets rotated in this direction and lengthened. So it's rotating and it's getting longer. Okay. Well, the next question is a little tougher. You said that the vector in the original space is unknown, but we know what it maps onto, which is 7, -4. Well, it's going to turn out that the vector that maps onto 7, -4 is 3, 2, but we don't know that at this point. So we got some vector which we regard as unknown mapping onto the vector 7, -4. So we have to look back here to see what that vector might be. We have to go backwards. So how do we do that? Well, we say that v1, v2 maps onto v1 plus 2v2, v2 minus 2v1, which is our rule, and that this vector onto which the unknown vector v1, v2 is mapped is 7, -4. So how are we going to find v1 and v2? Well, whatever v1 and v2 are, v1 plus 2v2 has to equal 7, and v2 minus 2v1 has to equal -4. That gives us two simultaneous equations. Okay, I'm not going to read them to you. Here they are. And we just solve them, and we solve them in this case using row reduction. We could also have inverted this matrix and multiplied by 7, -4, and you should be completely aware of that by now. But right there is the system we reduce, and when we finish reducing it, here's what we end up with, and that tells us that v1 is 3, v2 is 2, so it was the vector 3, 2 that mapped onto 7, -4. Now what we actually calculated was the inverse transformation, the vector here that maps onto this one. Okay, so now we have a picture of at least part of this linear transformation. The picture tells us that this vector 3, 2 maps onto this vector 7, -4, and this vector 2, -3 maps onto the vector -4, -7. Well, we can combine those two results into a single picture, and let's color code it. This will be the vector 3, 2 that maps onto the vector 7, -4, and we've coded that in orange. And also then the vector 2, -3 mapping onto -4, -7 we've coded in yellow. So what do we see? Well, we see that each of these vectors gets rotated in the counterclockwise, in the clockwise direction, and each vector gets longer. Both vectors get longer, and the angle between the vectors, now maybe that angle stays the same, maybe it doesn't. This is a hand sketch. It looks like the angle might stay the same, so that you just rotate these in each one lengthens, maybe not by the same factor. Okay. Now there's another thing that I can actually conclude, and this is kind of a little prelude, but since you might be looking at this video for review, I'm going to throw this in, and this might be useful to you, that the area here is clearly greater than the area here. Okay, so I'm going to say that the area factor, this is in parentheses, it's not something you have to know right now, and you're not going to understand yet why, that the area factor is the determinant of the transformation matrix. Transformation matrix being 1, 2, negative 2, 1. Now we understand that this is the transformation matrix because if we multiply 1, 2, negative 2, 1 by well, not by 7, negative 4, because that's not what we did here. If we multiply the 1, 2, negative 2, 1 vector by the vector 3, 2, we will get 7, negative 4. That's the vector. That's the that's the vector equation. 1 times 3 is 3. 2 times 2 is 7. That gives us our 7. Negative 2 times 3 is negative 6. 1 times 2 is 2. Add up, you get negative 4. Okay, so this matrix multiplied by the coordinates of a vector over here gives us a vector over here. And if this matrix is invertible, we can multiply the inverse by a vector over here to get the vector it came from. Now I'm saying the area factor is the determinant of this matrix. And in class we did a little estimate. I said, well, this vector is about twice as big as this one, and this vector is about twice as big as this one. So this triangle might be about 4 times as big as this one, since we have double the base, double the altitude, assuming the angle stays the same, and we can't assure that, but it might be the case. Okay, well, it turns out that this determinant is what? It's 5. So I estimated, just ballpark, that the area factor ought to be 4. Turns out it's 5. Another thing you get out of the determinant, if we rotate from the first vector to the second, and then we look at where the transformed first vector and transformed second vector are, we'll rotate in the same direction to get from this vector to this vector, provided this number is positive. If this number was negative, the direction of rotation would be different. We would have to rotate in the clockwise direction to get from this vector to this vector, but we would rotate in the counterclockwise direction to get from the transformed vector to the transformed vector. Okay, they would go in the opposite direction. That's not what happened here, because the determinant is positive, but that's what would happen if the determinant was negative.